Welcome to lecture 4.4, where we're going to be discussing resonance for heteroatoms. So we're going to handle this very similar to how we handled negative charges, and that's going to be with an emphasis on these bond to atom and atom to bond arrows. There is one key difference, however, and that key difference is that heteroatoms, such as oxygen and nitrogen, which are the main ones we're going to be seeing in this course, are not always negative with lone pairs. And this is an important consideration. You can look back to section 2 to remember about the formal charges for oxygen and nitrogen, recalling that oxygen is actually its neutral form when it has two lone pairs, and that nitrogen is in its neutral form when it has one lone pair. So we're still going to be able to move these lone pairs. Even when neutral, this is still a loosely held pair of electrons in all cases. However, when we were dealing with carbon, the negative charge really helped instruct us on how we were going to draw the resonance. So sometimes heteroatoms can seem more difficult, but really it's the same kind of idea. So let's take a look at some oxygen resonance forms. Now, for the top molecule, this is a molecule that doesn't actually have a charge. I'm going to highlight the loosely held electrons here in red, so both lone pairs on the oxygen and the pi bond of the carbonyl. Now, take a quick second and try to remember what the functional group name is of this molecule. The answer is that this is an ester. You can tell it's an ester because we have one carbon that's double bonded to one oxygen and singly bonded to another, but that oxygen is connected to a carbon instead of a hydrogen. If it was a hydrogen, it would have been a carboxylic acid. Moving forward, we can see that this molecule right now is neutral. And remember that resonance typically isn't that useful when we're looking at neutral molecules. So let's see if that follows here with heteroatoms as well. Now, remember that we need to move these electrons in a way that is going to put them in a good final location. So for example, one resonance form you might try is to move the pi bond. We might say, well, let's move those electrons to the oxygen. Well, we can give that a try. This resonance form is going to look something like this. So the two electrons of the pi bond have now moved to make this oxygen negative and sp3 hybridized. And that's also going to leave a positive charge on this carbon down here. Now, comparing these two resonance forms, it's clear that the form on the left is much more stable. Now, going from this resonance form, we could have done this directly, but we'll start from here. Let's try moving these lone pairs on the oxygen. Right, now that we have a positive charge adjacent to that carbon, or adjacent to those lone pairs, we're going to be able to move that lone pair between the oxygen and the carbon, making a bond between those atoms. So this is going to look something like this now, where our oxygen up here still has its negative charge. But now what we've done is we've made a double bond to this oxygen. And it's still connected to that carbon. Remember that without the arrows telling us to move something, it's all going to stay put. Now, this oxygen was neutral, but actually traded its lone pair for a bond, which means this oxygen is now going to have a positive charge. So, once again, comparing all three of these resonance forms that we've made that follow the rules, it's clear that this resonance form is the most stable one. It doesn't break the octet rule like the one in the middle does, and it doesn't have extra charges like this one does. Considering that, one way we could view this is that this molecule here represents the major resonance form, and these represent minor resonance forms. We'll talk more about this in the next lecture, lecture 4.5, but for now, the main point I want to illustrate here is that since this molecule was originally neutral, we're not going to have amazing resonance stability because of it. However, looking at this case, we now have a deprotonated carboxylic acid. Another word for this is a carboxylate. And that gives us a negative oxygen down here. So if I use these electrons to make a bond. This is an atom to bond arrow. That's going to mean that this carbon is too full, but lucky for us, we have some loosely held electrons there that we can move up to this oxygen. Drawing the resonance form here, that means that this carbon, or the oxygen down here, is going to be neutral, and the oxygen up top is going to be negative, kind of changing the charge. Now, what this leads to is a resonance hybrid that takes 50-50 character, because these are equally stable, they're both the same, and spreads that negative charge across the two oxygens. -1/2 charge on each, -1 charge entirely. So comparing that oxygen and this molecule to a molecule like this, we would say that we expect this molecule to be far more stable due to the fact that it really has another major resonance form. These are both major. And that they form a resonance hybrid that is much more stable than just one localized negative charge. Again, the key idea here is this localized charge is going to be unstable compared to a delocalized charge that's been spread out via resonance. So that's oxygen. Let's take a quick look at a couple examples of nitrogen. Now, here's another neutral molecule that we'll take a look at for the first example. We can see that we have a nitrogen with a lone pair and a pi bond here as well as lone pairs on the oxygen. Again, remembering that we can only move these loosely held electrons. Let's do some electron pushing this time, and I'll take this lone pair and move it towards this double bond. Now, that would mean that this carbon in the middle is too full, but we can push the electrons from the pi bond up to the oxygen. Drawing this resonance form out, you can see that there's a new pi bond between the carbon and nitrogen here, and now a singly bonded negative oxygen up here. Looking at the nitrogen, we can realize that it was neutral with its one lone pair, but it traded that lone pair for an extra bond, and nitrogen with 4 bonds is positive. So once again, starting with a neutral molecule here, in this case, this is an amide, you can see that we've generated charge, and therefore we could call this a major form, and this form minor. Looking at this molecule, we can see that the nitrogen is neutral with one lone pair and 3 bonds, and we have a negative oxygen over here. So one thing we could do is move this oxygen, one of these lone pairs, to the nitrogen. Now, nitrogen doesn't necessarily have room for that, but if we look here, there is still another carbonyl connected. So if we didn't have that carbonyl connected, this resonance form couldn't happen, but since we do, we can make room on the nitrogen by pushing these electrons up to the oxygen. Here we can see that this nitrogen is now connected to the negative oxygen on the top and double bonded below. Very similarly, we can imagine such a resonance form with partial double bonds and the charge split between the oxygen atoms. In this case, the nitrogen acts quite like a carbon. So we can see that once again, when a negative charge is in the molecule, resonance stabilization plays a factor. Now, in the next unit, let's dig into this major and minor form idea a little more to find out exactly where we draw the line and what makes one resonance form better than another.